So thanks everybody for sticking around. How many people here came just to see whether or not I was overselling with the title of this talk? Is there any? There's one. So hopefully by the end you'll see that I'm not overselling it. To quote Peter Thiel, look for irreplaceable work on a unique problem alongside great people. This is really irreplaceable work on a unique problem with some really cool H2O powered modeling. Okay. So I'm going to start with just an outline of the talk. I'll give you a brief background of my background, how I fell in love with H2O, and I'll only go to T-2 here, and give you a brief history of ledger investing and why we chose H2O here. I'm going to give you a mental model to walk away with what we're trying to accomplish, this transformation that we're trying to accomplish in the insurance industry, and talk about our solutions of the insurance value chain, two of which are powered by H2O. I'm then going to focus on one of these solutions called stochastic loss reserving, and I'll define what that is in the context of insurance. I'll give you a primer. I'll go through some exploratory data analysis, some of the machine learning techniques that we've used, all H2O powered, the results of those, and then how the results are used by investors in our platform. Okay. So I started to use H2O while I was a computational and technology lead at the Broad Institute of MIT and Harvard, working in genomics, specifically network biology, building a large-scale platform called GeNets for learning topological properties of biological pathways so that biologists could better elucidate the biology underlying their experimental data. So it actually wasn't until after I built this platform that I learned about H2O. And so I know what it's like to build a large-scale platform using machine learning, powering the analytic layer with an offering that is not product-centric, okay? It wasn't until after this that I learned about H2O. Thankfully, we were able to develop other methods very quickly with H2O. For example, the first method to infer protein-protein interactions directly and solely based on gene expression data. So after this, I was the chief analytics officer at Apptopia, a leading mobile intelligence company, where we re-architected and implemented the analytic layer all with H2O. So we were able to increase the predictive power across 20+ machine learning models that really constituted the core value proposition of Apptopia, leading to significantly greater predictive power in less cost and less time. So it fundamentally transformed the way that we were able to compete in this market. I presented this, what I call the H2O and Spark love story, at the Spark Summit last year, and I've included here a link that you can go and reference there and look at the video and see this transformation we were able to complete with H2O. So I've architected and built large-scale ML SaaS offerings without H2O, and I've gutted and rebuilt them with H2O while growing a company and an analytic group. So when I first started talking to ledger investing as an ML consultant, and then after that as the head of product, the choice was very clear on what we can use in our tool chain. So what is ledger investing? Ledger is really a platform for securitizing insurance risk. Okay? We use technology and AI to empower and unite insurers and investors from the capital markets to transfer risk from the insurer's balance sheet to the capital markets. This fundamental transformation in the insurance value chain will create value for the insureds, those that buy insurance, the insurers, and the investors. So I'll just give you examples of each. So insurers, by lowering the cost of capital and the ability to flex that capital with swings in market prices. Investors with greater transparency of the actual underlying insurance risk, greater diversification for their portfolios, both of which have the potential to increase returns. And finally, the insureds, an optimized capital structure will translate to a decrease in the insurance gap, the difference between economic losses and what's insured, and also the ability to better price that risk as well. So since we're in the Valley, Ledger is really a tech company with Silicon Valley roots. It was founded by Julian Bressano and Amir Rabat. They became YC fellows and started talking to the former chief risk officer at AIG. His name is Samir Shah. Samir spent his career at the intersection in the insurance industry and capital markets. So all three of them went through the YC winter class of 17, and they emerged with funding from Excel and others. So you can think about it, there was really two forces coming together here. You had an industry insider, spent his life in the industry, and two young hackers from the Valley that wanted to try to find a way to disrupt this industry and create more value. So to give you a mental model to walk away with how we're trying to transform the insurance value chain, just think about it as insurers are really an intermediary between the insureds and investors. So they house capital on their balance sheet, and what we want to do is take that capital off the balance sheet of insurers and provide the technology and the analytics and the legal mechanisms to offer that to the capital markets. So we do this with three solutions. So first, the risk modeling, increasing transparency of insurance risk drivers at the policy level helps insurers understand the economics of their book of business across different lines and coverage types. This is the kind of stuff I actually cut my teeth on out of grad school working at Allstate Insurance, building rating plans. We take it several steps further because we need to do some unique things to be able to securitize these things. And I'll talk about this, and this will become much more apparent later. Second, stochastic loss reserving. This is going to be the bulk of my talk when we get into the applications that we used H2O. So this needs a little bit of an introduction. In insurance, you have losses and premiums, okay? The premiums you get at the starting of the policy, but the losses you might not get for several years. Depending on the line, it may be up to 10 years where you don't actually know what the total losses are for that specific accident year. So losses are said to develop over time. This is due to many factors. The efficiency of your claims processing, the litigation in that state, and so on. And you're going to hear something called a loss ratio. This is losses over premiums, and this is what we're going to be modeling. Okay. So insurers want to minimize that loss ratio. So for both the loss modeling and the reserving, we've been able to harness H2O as a key ingredient along with other really ideas and paradigms from actuarial science, Bayesian models, time series, et cetera, to build a foundation for a suite of proprietary methods that enable us to model this risk, make it more transparent, and design it in a way for securitization. So the securitization, these analytic capabilities really coupled with the technology stack and the legal structures give us this mechanism to take those liabilities off of the insurer's balance sheet and open it up to the capital markets. So H2O powered stochastic loss reserving. I'm going to start with a primer on, I'm just going to denote it SLR, stochastic loss reserving, for the remainder of this talk. I'll give you some exploratory data analysis on loss development and the loss ratio distributions. I'll talk about the methods that we employed to model this loss ratio and loss ratio development and their performance versus conventional methods. And then I'll show how these results are used by investors to make investment decisions. Okay, so a primer on SLR. In this table, you're going to see on the far left just accident years. So from 1989 to 1998, 10 accident years. I'm going to introduce this concept of an AY index. You'll see that it's the distance away from that last accident year. You can think about it as 1998. If we were in 1998 filing year, it's the distance away from that filing year. Each year, you know your net premiums, and these are in thousands. And then you have your losses, and then in the final column, you have the loss ratios, the losses over premiums. Again, insurers want to minimize this. As it approaches 1, your profit is decreasing, and over 1, you're losing money. Okay. So I sort of hid something from you. I've alluded to the fact that losses develop over time, sometimes up to 10 years and more of these losses developing due to litigation, claims processing, et cetera. So what I'm going to do is I'm going to expand this table. Just take that first row of that 1989 accident year. Net premiums have not changed. The final losses, this is actually 10-year losses, has not changed. But I'm showing the development lag from 1989 to 1990, 1991, 1992, et cetera. And you see how these losses develop by year. Okay? So that was just for 1989. I'll unhide the rest of the table. And you see that each one of those accident years has its own loss development. Okay? So right now you're saying, you know, have you heard of visualization? Can we see a visualization? Yes, I have, and yes, you can. So this is what it looks like. This is really what the modeling problem looks like. You have these loss trajectories, and they're colored by accident year. 1989, that first row is at the top here. So you see that they're really trajectories that develop over time. And after 4 or 5 years, they converge somewhat. Okay? So, but what if we were in 1998? So we really have incomplete development trajectories, because looking back, I was able to show you that complete loss development table. But if we were in 1998, we don't know the next year and the next year and so on. So what you really have from a modeling problem is modeling and projecting out these trajectories for each of the accident years, whether you're missing that final year or 2 years out, 3 years out, et cetera, to actually know the full loss development landscape for a specific filing year. So this is what we would have looked at if we were in 1998. Okay. So this was for a specific insurer, but I want to take a step back or go a step up and look at this from an industry perspective and help you better understand these loss ratio distributions and development over time, and how systemic factors also evolve. Okay. So first, I'm going to show you loss ratio development by the lag. So those new columns that I first hid and then introduced. So we're looking at loss development, those loss ratios. The x-axis is the loss ratio. You see it goes from 0 to 1.5. And by the development lag, you'll see that this distribution converges based on development lag 1, development lag 2, 3, 4, 5, 6, and so on, all the way to the 10th. So you see that it somewhat stabilizes and converges, just like this is a different way to think about how those trajectories converged as well, but we're looking at really a holistic level from an industry perspective across many insurers. Okay. So next, I'm going to show you, again, from 1989 to 2007, and I'm going to show you the distribution, the density of those loss ratios by accident year. Okay, so this is on the first panel here, and you see really the structure of this distribution evolves over time. The mean evolves, the standard deviation evolves, the structure evolves. You can think about, just for a mental model, the best model that we've found for loss ratio is a log normal model. The mean is 0.7, standard deviation of 0.2. Okay, but that's if you're looking across all accident years. But you certainly see the changes in the structure of this distribution by accident year. So if I take this one step further, if we assume that log normal model and I want to bootstrap the distribution for the mean itself, the mean parameter, you can see now we're on a different space here since we're modeling the mean itself by accident year from 0.5 to 0.85. But again, the uncertainty around this mean changes, the location changes as well. So the other parameter, the standard deviation, follows this as well. I just want to note the space that we're on, now 0.1 to 0.3, because we're modeling the standard deviation of this distribution. So you'll see that this evolves as well and gets very tight at the end. Okay? So the uncertainty around the parameter estimates are changing. The nature of the distribution is changing as well, systemic factors as well as company-specific factors. Okay. So to model those trajectories, we've used many methods from H2O, from using the R API. Now, I'm going to go directly into the performance of these methods. We really have standard conventional methods from the actuarial community, and I'm going to be showing you specifically about how these new machine learning approaches compare to the actuarial methods. But I would really think of it as, and we think of it as, that we're building on the shoulders of actuarial giants. We're taking ideas from actuarial science, we're adding in methods, Bayesian methods, ML methods, time series methods, to come up with these new ways of getting better predictive power. So in this table that I'm going to show, the columns are performance metrics, the average absolute error, root MSE, and the sum of the absolute errors, because the first two are really collapsing down that information into one metric, but the nature of our problem is we really want to have a good understanding of the total mistakes that we're making as well. Okay? And this is the same in many spaces. Within each one of these cells, it's really the ascending rank of ordered models. So because we're quantifying the amount of mistakes that we're making, we want these bars to be smaller. And the methods here, the blue is going to be the machine learning approaches. So we're using about 6 approaches, 5 or 6 approaches, and then 6 approaches from conventional methods. Okay? So holistic picture of performance, the salient feature that I want you to see, we're really focusing on this part of the graph. And we're focusing on this part of the graph because remember that AY index that I introduced. So those were the years for which we had either 1 or 2 or 3 years of development. So the full loss trajectory, those trajectories that we wanted to predict out, were the most undeveloped. So that's where most of the uncertainty is coming in the loss reserving problem, whereas the other trajectories have already converged. So in terms of the marginal value of building models to predict out for each one of those AY indices, this is where most of the value comes from us. And this is really where the ML approaches shine. So the ML approaches are the blue bars. The bars constitute the total amount of errors that we're making. And you see, to use game theoretic language here, they strictly dominate in these 3 accident year indices that we're trying to predict out. So if we're trying to predict out 9 years, 8 years, 7 years, et cetera, they dominate in those accident years. So I'm just going to zoom in here so you can get a better picture. This was the same graph that I was showing before, and this is the relative performance of those years. Okay. Now, everything that I've talked about so far is all about expected value, right? In a lot of the machine learning problems that we have, this is the end game, the modeling the mean. But specifically for securitization, this is only, as G.I. Joe once said, this half the battle, okay? So we're really interested in the full probability structure of that distribution and forecasting the probability structure of that loss ratio over years, okay? So we need the full predictive distribution. So here I've labeled, if we were thinking about the structure, the nature of this distribution, this loss ratio distribution over the development years, the underlying reality, if we think of it as the dark distribution, and we need to come up with a predictive distribution, both a mean, the structure, and an understanding of the variance. If this is a non-parametric model, we need to have an understanding of the structure. If we assume that log normal model that I talked about, we have to have a good estimate for both the mean and standard deviation. Okay? So we care about this, the whole structure of the distribution, and we care about the whole structure because this is how investors are going to use these distributions. They're going to segment these distributions called tranching, and they're going to accept the risk if the loss ratio falls in a particular section of this density. Okay? So they're really making investment decisions based on the probability structure that we're forecasting. Okay? So to do this, we integrate the ML methods with ideas from actuarial science, with other Bayesian techniques, time series forecasting, to not just model the expected value, but to forecast the entire predictive distribution at lag 1, lag 2, et cetera. So how is the performance not just, so I showed really strict dominance in the most important accident years for modeling the expected loss ratio for the most important undeveloped years that we have. If we have the predictive distribution right, that means the entire distribution right, that means that the percentiles of the predictive distribution that we have are going to be uniformly distributed. Okay? Percentiles of a specific probability distribution, underlying probability distribution, are uniformly distributed. So we can test this out, and we have. So if you take a look at our best ML method, unifying ideas from all of those methodologies and paradigms, we have these two distributions of the underlying percentiles. In the green right now is the best ML method, and I just realized that the colors are mixed up, and I apologize for that from the previous graphs. The best conventional method is the blue. So you see that a lot of the predictions are showing up in the lower tail. So these are, again, on the x-axis percentiles. So we're trying to approach uniformity of these percentiles. We still have a little bit of way to go, but in terms of how investors are making decisions based on these predictive distributions and the structure, if you take a look at the tail, the 100th percentile, this is something that we really don't want to be bad at, right? So we do not want to spike at the other end, and this is where the ML methods are doing even better than the conventional methods. You can take a look at this also from through the lens of a PP plot, and this is another thing we do when testing our methodologies for building these predictive distributions. And so that is the nature of the problem, how we're building these models. Not just the expected value for the loss ratios, but really building out the entire predictive distribution, because that's what investors are going to be making investment decisions on. I think from data scientists to executive, we all make very important decisions about how we create lasting value, and the tools, the platforms, and the code that we build a business with. So for many years now, I've used H2O. It's been a big component of how I and my colleagues have created a value in a variety of spaces. And it's because I firmly believe H2O is an AI horse to bet on. This is why we chose it as an important ingredient in the analytics that we use to create the potential to be a $1 trillion asset class at Ledger. Thank you. Sure. Can this model reinsurance risk transfer? Yeah, this is a good one. So the cat bond market is actually, so this is all motivated by insurance. You can think of this under the umbrella as insurance-linked securities, and the cat bond market is really the start of insurance-linked securities. So yes, it can, it has, it's proven it, it's paved the way for what we're trying to do with transforming the value chain of insurers. So certainly this is related to cat modeling. That's the only one. No? Okay. Thank you.